we're going to be talking about chemistry here in a little while. This is chapter 2. This is like introductory information. It doesn't seem to make sense that we'd be talking about it now, but if you really think about it, we got a lot of stuff going on inside our bodies that is completely chemistry based. The molecules that we're made of, like the fats, and carbohydrates, and proteins, and nucleic acids, all of which are made of atoms, right? They really do make up everything. You can't trust atoms. Okay, sorry, corny joke. Anyways, matters exist. These atoms, these molecules can exist in different shapes. If they're really, really packed together and they're bound together really nicely, they could be solid. If they're not really holding on to each other really fantastically well because of heat or, well, I don't know, whatever, it could be a liquid. And then you have the ones that are really sparse and far between each other, a gas which we breathe just fine. Elements are things that, well, how do I say this? It's a special type of atom that an atom is composed of protons, neutrons, and electrons. These protons, the number of protons that you have determines what type of element you have. Hydrogen has 1 proton, carbon has 12, things like that. It just helps explain and tells you what's going on. And based on the size of those protons, it determines how many electrons you have. You got a lot of different elements going on too. You got oxygen, carbon, hydrogen, nitrogen. These ones down here called the lesser elements for some reason, mostly because it's just not much high in quantity for our bodies based on body mass. You got calcium, phosphorus, potassium, sulfur, sodium. Kind of makes sense. Calcium, right? I mean, our bodies, our skeletons are made of calcium phosphate. So you would hope that it's quite abundant. You also have trace elements, like for instance, you got silicon hanging out, some of us a little bit more than others. You got iodine, you got copper. You'd think copper wouldn't be a part of you, but yeah, you need to ingest little itty bits of copper, and no, you don't actually have to ingest a penny to get the amount of copper you need. Most of the foods that you need already have copper in it, and you'll be fine. So we do need to talk a little bit about how these atoms interact with one another. Now, one atom they really, really want to be happy. And in order to be happy, they have to have these little electron shells filled completely with electrons. So there's a couple of ways to get these electrons. They could steal it, they could give it away, they could share it, you know, things like that. And when they do that, they could become they could be ions, they could be molecules, they could be compounds. We're going to talk about a couple of these chemical bonds really quick. So first off, let's talk ions. Ions are the ones that form ionic bonds. Ions are things that are charged. They have a positive, they could be negative, they could have 2 positives, they could have 3 positives, they could have 2 negatives and 3 negatives. What that is inferring is electrons are negative, so the ones that are negative like stealing electrons. And the ones that are positive like giving away the electrons. And just like a magnet, if there's a positive, the positive is attracted to the negative, so it makes an ionic bond. So an ionic bond is one of these guys steals an electron, becomes negative, and this guy goes, wait, give it back, and they follow each other. Just like a magnet would follow a negative end and a positive end. A covalent bond is when the 2 atoms decide, hey, you know what would be cool? Let's share this electron. We can share them, we can be happy, we can both be happy, we don't have to have positive or negative charge. It's great! It's wonderful! So a covalent bond is sharing an electron. You can share multiple electrons. So look at this, hydrogen sharing 1, oxygen sharing 2. If you got 2 nitrogens hanging out together, they can share 3 electrons, which is pretty crazy, actually. Now, there is sometimes where, kind of like a big brother and little brother, big brother, little sister type of thing, or big sister, little brother, where the bigger one really likes to hold on to electrons a lot more than the little ones. Like, sharing isn't their forte. They're trying, but they're not doing a great job. Big brother decides, hey, I want to play video games, and so does little brother. And big brother plays the video games for like 30 minutes, while little brother plays it for like 5. And big brother thinks that's equal. And little brother doesn't realize that that's not what's going on, but hey, it's happening. And when that happens, if this oxygen is holding on to that negative electron for a lot longer, it becomes more negative. That hydrogen becomes a little bit more positive in nature, even though it still has its electron. Which sort of explains why the liquids really hold together. Like liquid water holds on to each other really, really nicely, because you got a negative end and a positive end, and those positive ends, those positive hydrogens attached to the water molecule, sure does like the other oxygen, and they orient each other. Because of that, this is called hydrogen bonding, by the way. This is the strongest form of intermolecular bonding. You're going to learn about that in chemistry. If you haven't learned about it, or you have taken chemistry and you don't remember it, just pretty much hydrogen bond's strongest intermolecular force without actually forming a bond or sharing an electron or taking an electron. What that means is that water can hold on to each other really easily. You can put water, if boiling point is really high for water, it's like 100 degrees Celsius but 212 degrees Fahrenheit, while still freezing at 0 degrees Celsius or 32 degrees Fahrenheit. It's really impressive, actually. A lot of different substances don't do that well. Now, let's just go ahead and make this video like a chemistry introduction. So this is the chemical reactions that you could have. So let's say you do want to start exchanging, swapping hydrogens and oxygens, changing some bonds and things like that. What happens is one side is the before and after picture type of thing. This was Jeremy in high school. Look at him in college now. That's amazing. So first you have the reactions, the reactants, and then they interact with each other and they form a product. Look at this beautiful new product. The ending substance. Now each one of these reactions, well, it requires energy or can give away energy. Most of these reactions require some type of energy to occur, or else everything would explode, pretty much. Diamonds, they would fall apart and become like graphite, like the pencil lead. But because of the activation energy, the energy to be able to do that is a lot higher, it doesn't really want to. So it stays as a diamond. Enzymes in your body help lower that down. Which is a good thing because, well, sugar doesn't really like being broken down for energy either, and it would take about 10,000 years for it to happen naturally, without any outside source. So really, we don't really have that much time to wait for those sugars to break down. We kind of need it instantaneously. Enzymes or catalysts bring down that activation energy so that it's easy to get over that hump. Now, an exergonic reaction is the net release of energy. The net energy taken out is given out into the environment. Well, an endergonic reaction is one that absorbs it and keeps that energy. So you got different types of chemical reactions. I'm assuming most of you are familiar with synthesis, which means to make. So like synthetic oil, you've made this oil. Decomposition, maybe decomposing things, especially in New Orleans. You can ride your bike down the street or walk down the street. Maybe some ditches are open. You can smell some of the creatures that were unfortunate, and yeah, they're decomposing. They're coming apart. So decomposition just means break apart. Exchange is, well, I'll give you this for that, and it happens. Reversible, which is most of the stuff that we do in our bodies, or the enzymes do in our bodies, is you can go to a product or you can come back to a reactant if you want. And then redox reaction, that's more of the stuff that is like rust. You're giving oxidation is losing an electron, reduction is gaining an electron. So with that, let's talk a little bit more about water and how come it's really weird. This is such a strange setup, but I'm going to go ahead and continue following with it. Mixtures, water is fantastic. Remember, it has that positive negative charge. Anything that has a little bit of a positive or a negative charge, that dipole-dipole moment is the word. You don't really need to know dipole-dipole moment. Don't stress over understanding dipole-dipole moment or that word and memorizing it. But it allows things to get dissolved, especially ions, right? So ions are positively charged, so, well, if ions have that negative and positive charge, it just helps out in dissolving those. There are things that don't like being dissolved, like fats, but we'll get to that here shortly. Or dissolved in water, like fats. We'll get to that shortly. But first, let's talk about pH. Let's make certain we understand pH. pH, ignore this top part. Don't worry about the blue. Just worry about this stuff. This is what we usually refer to when we talk about pH. It's on a scale of 0 to 14. You can go below that, you can go a little bit above that, but we're not going to go into that right now. What this is saying, 7 is neutral. The smaller the number, the more acidic you get. So like our stomach acid is like 1 to 2, maybe 0 every so often. Carnivore stomachs have a 0 to 1 type of region. Herbivore stomachs are like 2 to 3. You also have acetic acid, which is up here, so is soda drinks and all that. When it's not concentrated. Concentrated, it's a little bit down here, a little bit more. Basic solutions are higher than 7. 8, 9, 10, 11, 12, 13, 14. They too like to eat substances, but it's in a different way. But our blood is a lot closer to 7. It's at 7.35 to 7.45. Not super important for you to know that now, but MP4, yes. So I guess if you're good at memorizing numbers, go ahead and memorize it now. 7.35 to 7.45. And here's a list of stuff that, and their pHs. You don't need to know this. It's really unimportant to know this. It's just examples of the different types of pHs. You can see that gastric juices, again, like I said, is like 1 to 2. But here's some other stuff. We don't need to know that, all this, though. Let's go ahead and pause here. I'm going to go ahead and create a new video for the organic compounds. And then we'll segue into the large biomolecular compounds there. And that'll be the ending of this discussion for chapter 2. Thank y'all.